Breadth-first search has been able to find the shortest path by going down in breadth-first fashion. And once you find the goal for the first time, you know that it has been the shortest path to get there. Now, if you have edges which have different costs, so you have edges which might have a very high cost and edges with a very low cost, then you might go down an edge with a very high cost first, and you arrive at the goal, but you haven't seen the edges with the lower cost yet. So to best mimic what breadth-first search does is to choose the node that has the lowest cost to the start. There's an elegant data structure to help you with this, which is called a heap. In a heap, you can store things sorted based on some other quantity, some other metric that goes with it. And so we can store our nodes with the cost that is associated with it. And for that, we need a different library that we will import, and that is known as heap_queue. And we import heapify, which turns a queue into a binary tree that is sorted by the cost, and heap push and heap pop, which are functions to push something onto the heap so that it's sorted right away, and pop it from the heap so that it's sorted properly. Now, if we want to have a queue, we can define it as before, but now we say heapify queue, which will sort the queue. And now when you load up a node into this, or maybe even have two nodes in here, then the heapify function will just sort them based on their value. So that will sort them based on the ASCII value of these characters. This is not what we want. What we want is to sort them based on cost. And the heap_queue library, you can do this by providing a tuple, and the first value will be the number that heap uses to sort. So if you have a heap like this, the heapify function will sort it so that this tuple, which has 0 first, comes first, and then the tuple with the 2 will go second. If you would say something like heap push q, and you push another tuple, let's say 0 and c onto it, then the heap push function will put it at the beginning of the queue because it has the lowest cost. Actually, that's not true. Let's do it this way. So in that case, heap push would put C first, B second, and then A. Now, in order to introduce the cost here, we need to maintain distances. And if A is the start node, then we want to add a 0 here so that the algorithm knows there's no cost to get to A. And let's say we want to go back to F later. But now the question is, where do we encode the edge costs? Now, we have already defined the graph, which you see here. And what we have is to go from A to B requires 5 steps. And so what I can do is I can introduce tuples like this, where the first entry is the cost and the second entry is the previous label name. So now if I traverse this graph, I can always retrieve not only each child, but also the cost to get to it. So we have a 5 here again. Alright, now I have added costs to each of the edges, and we can see what else we need to do to implement Dijkstra's algorithm. So again, the first and most important step is to turn the queue into a heap so that I can sort it by distance. But what I also need to know is I need to keep track of the distance from the start node to every other node in the tree. And for that, I can introduce another dictionary, which I call distances. And this is going to be a dictionary. But what I want to do is I want to create default entries for every node to be infinity. For that, there is a data structure called the default dict, and I can provide a lambda function with it that will return infinity for every entry that is not known yet. And I need to import this from collections. And now we have a default dictionary where I can retrieve the distance to any node in this data structure, in this graph, without having to actually create a for loop and looping through all the keys and then adding them and adding infinity. I could do this as well, but default dict is a little simpler. And now I can say that the distances to the start node are 0. Alright, so let's have a look at how the algorithm works. Let's remove these data structures from the previous one. I run the same algorithm. I have my heap queue. I iterate through it until it's empty. Now instead of popping directly from it, I use the function heap pop. And instead of a single node, I'm getting also a current distance. So I'm getting a tuple whenever I pop from the queue. And now I don't use the getNeighbors function just yet, but I again pull from the graph. And now when I pull from the graph, I don't just get a node, but I again get a tuple. And the first entry is the cost from V to U. So if I look at the node V, what I'm getting are its children and the cost to it. So it's the cost from V to U, and I get the node U. Now I haven't defined the visited list yet. Let's add it here, and I include the start node here. Alright, so what else do I need to do? Once I still have something in the queue, I get the node with the currently lowest distance. In that case, I will get the start node. Then I will look up the neighbors of the start node, which is the B node and the C node. I will retrieve the costs to it. And I will now only take those nodes that haven't been visited yet. So what I should do is I compute the new cost that it would take to get to the node, and that is the distance to the current node, which is V. And you remember this is the start node, so this is 0 plus the cost VU plus the cost to go from A to, in this case, B, which is the first one. So this will be 5. Now you remember I initialized all the distances to be infinity. So I have now found a better way to get to B. So I can say if the new cost is smaller than the previous cost to U, then I want to overwrite that and set it to be the new cost. So now B was at infinity. Now I know I can get to it in 5 steps. Now I want to add this node to the queue, but in this case I need to use the function heap push because I want to put it onto the queue in a sorted way, and I want to use the new cost as its distance. I will say that I visited, and I say that I have a new parent for U, which is V. And also here I need the parent data structure, and what we've done so far is we just used an empty dictionary to store the parent. So let's see what happens when I run this, and I have to tell the heap push function what the data structure is that contains the heap, which is this one, and I get a result which is ACF. Now we can check the picture of the graph, and we see indeed ACF is the shortest path to the goal, which is 6. The other path going through B and E would be 7. Now we can change the cost from A to be 2 and see what happens. And now we expect the Dijkstra algorithm to return A, B, E, F. Let's see if that is the case. That is not the case just yet. And the reason is, when you look at the description of the algorithm, you will find that the visited node has to be added right away. And I have to actually add it to the visited queue as soon as I actually visit it and not just discover it. So if you do it that way and run the algorithm again, you get the correct result and you go from A to B, then to E, and then to F. In order to understand why Dijkstra is not finding the shortest path unless we add the node to the visited list only later, let's print the queue and look at what the heap actually produces. So the first entry on the heap is the node A at cost 0. It then discovers nodes B and C at cost 2 and 3. It will pick the one with the lowest cost, which is node B, discover the nodes D and E. Now the heap is being sorted again, and you see it has nodes E, nodes D, and node F at cost 3, 5, and 6. And now you will see that it actually never discovers the shorter route to node F. The reason is that we have added F already to the list of visited nodes here, and what we should do is we should only add it to the list of visited nodes once we actually explore it. Now if we run the algorithm again, we will see that the algorithm indeed finds the shortest path that is now going via B.